These are super popular. We have 1, 2, 3, 4, 5 mass spectrometers downstairs in our instrumentation suite. 2 of them are what's the word? Dedicated detectors for gas chromatographs. 2 GC mass spec systems we have. Our laboratory work next week, 2 teams will be working with those mass spectrometers, just ignoring the GC part of it, just working with mass spectrometers. A third one is a standalone, pretty nifty mass spectrometer that can accept ambient pressure gaseous samples. The other team will be working with that one. They're all similar in terms of the ion sources. They all have electron ionization sources. And mass analyzers, they all have quadrupole mass analyzers. Right? Some people refer to those as quadrupole mass filters, right? Because it achieves basically that sort of a function. Kind of difficult to see here. I attempt to impress with the differential equations. This describes the relationship between the force applied in various directions to the trajectory followed by a given ion. But if I can just give you the warm, fuzzy, big picture, ions are introduced to the quadrupole region there between these 4 big electrodes. The electrical potential of those electrodes are, the potentials are ramped linearly and varied sinusoidally over time. At any given point in time, the actual value of the applied DC potential and the frequency and amplitude of the AC potential will cause, well, it causes the ions to travel helical paths through the quadrupole region. At any point in time, any given value for the DC potential and the frequency and amplitude of the AC potential, only one or a narrow range of mass to charge ratio ions will successfully traverse the full region. Will travel in a helical path down through the center and exit that little circular slit at the end of the quadrupole region. All the others, they might be traveling a larger diameter helical path and collide with the electrodes and get annihilated. They might be traveling a much smaller diameter helical path, but not straight and curved, and hence miss the exit hole. Are y'all with me on this? And so again, it's a matter of inducing a change in the direction of travel based on mass to charge ratio. In this case, it's by a more sort of complex phenomenon. The parameters, I haven't really been harping on this, but they are here. I hope you guys review these slides, multiple times along the course of considering a given module's content. But these slides here hit on some of the basic figures of merit for these mass analyzers. Right? What is the resolution and range? Excuse me, are they relatively expensive or not? Well, quadrupoles are. You might think, yeah, we've got 5 mass spectrometers, and all the mass analyzers in those are quadrupoles. I mentioned the 2 GC mass specs, the one standalone gas phase mass spectrometer. We also have 2 mass spectrometers with different ion sources, electrospray, and then a nifty one we're not even talking about here, but we'll chat about in lab later in the semester, atmospheric pressure chemical ionization. But they are, what's the word, solids and liquids are amenable to analysis here, non-volatile compounds, right? The quadrupoles, real popular as mass analyzers for chromatography coupled instruments, hybrid instruments, GC mass spec, LC mass spec, etc. And last but not least, you can use mass analyzers that will generate a time-varying signal, not like the time of flight. This is different. These are not field-free, right? Ion trap type mass analyzers, where oscillating electric and sometimes in conjunction magnetic fields, sometimes it's both, will cause ions that are injected into the trap to travel in circular paths. So they are indeed physically trapped within the ion source until such time you are ready to eject them. But while they're in there traveling that cyclic path, you guys know how to make electromagnetic waves? You accelerate charge. You guys are aware that if there's a charged particle that's traveling in a circular path, it is constantly accelerating. That's centripetal acceleration. So depending on the angular frequency of travel for that particular ion, which is a function of its mass to charge ratio, it'll generate an electromagnetic wave that can be detected by these receiver plates. It's a time domain signal, everyone. Right? It's a time domain signal. How the intensity varies with time, it's a function of the mass to charge ratio. A Fourier transformation can convert that time domain signal to corresponding frequency domain signal, the mass spectrum that we care about. And it's not really frequency domain in this case, it's mass, but that goes all the way back to slide 1, where I mentioned that spectrometry, mass spectrometry is not really spectrometry in that strict sense in terms of involving interaction of light and matter. Although, you know, you could argue that this might be the one type where it sort of is, because the matter itself, which are the ions traveling in those circular paths, are generating light, electromagnetic radiation. It's sort of an emission process. So anyway, the important take-home relationship down here is that the mass to charge ratio will determine the frequency, the angular frequency of precession, the frequency of that generated electromagnetic wave. H is the magnetic field strength. You can vary that. These sorts of instruments, as I mentioned, they have to, the instruments themselves are FT type instruments because of the nature of the signal generation. It's a time domain signal. Resolutions can be really nice. Mass ranges, not too bad, 1 to 4,000 Dalton. That's it for the mass analyzers, everyone. As far as detectors, it is much less, I don't want to say sophisticated, much less exciting, I suppose. As a matter of fact, this is the last slide. And detecting ions is a transduction scheme, just like detecting photons. The simplest type of detector, least expensive, not as sensitive as others, of course, is the, I say of course, you usually get what you pay for. That is the Faraday cup. So an ion comes in, it gets neutralized when it collides with the wall of the detector body, right, across which is imposed voltage, and so that generates a current. Right? Current is generated every time an ion strikes and is neutralized by the inner wall of that Faraday cup, that collector as it's called, and the current is proportional to the, proportional to the charge of the ion. It should be independent of its mass and velocity, which is a good thing. So sensitivity is pretty uniform across the board. And then if you want greater sensitivity, electron multipliers. Analogous to a photomultiplier. Photomultiplier tubes are real popular for sensitive detection of light, photons. But the ions coming from mass analyzers strike the surface of some sort of emissive material, right, so-called dynode, and a single ion will generate multiple electrons being ejected. Those multiple electrons subsequently striking other portions of the electron multiplier device as they travel towards their ultimate destination of detection. And there's the cascade effect, just like in the photomultiplier tube case. You can get large gains. A single ion in can generate on the order of, what would that be? That would be 100 million times more. Right, so a single ion coming in might generate 100 million electrons going out. So huge gains are possible. Good for sensitive sorts of measurements. The sensitivities there, though, do vary with the mass and